Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. You'll get notifications for this series and many other ones on our channel. What we're doing today is video 4 in Multivariable Calculus, Chapter 1, Partial Derivatives. Section 1.1 is functions of several variables, and in this lecture what we're going to do is we're going to discuss functions of 3 or more variables, and then discuss level surfaces similar to functions of 2 variables and level curves. We're now going to discuss functions of 3 variables and level surfaces to get an idea of what the graphs of a function of 3 variables would look like in 4 dimensions. Our first definition is going to be for a function of 3 variables. A function of 3 variables, x, y, z, usually is a rule that assigns to every point x, y, z in a set D now, which is a subset of R3, a unique value w, which is equal to f of x, y, z in R. Just as before, we denote this by f mapping from D to R. D is a subset of R3, and the point x, y, z gets mapped to W. Before we proceed, now we're going to focus for the rest of the video, we're going to focus on these functions specifically. Before we do that, we'll give the definition of a function of n variables. A function of n variables, x1, x2 to xn, we use an index now because we don't know how many there are up to n, so at any dimension you want, is a rule that assigns to every point x1 to xn in Rn, in a subset D of Rn, a unique value w, which is f of x1 to xn, which is a real number. Again, we use the same notation. F maps from D to R. D is a subset of Rn now, and it maps these points to real number w. Now let's consider functions of 3 variables and level surfaces. Before we do level surfaces, let's look at an example of why it's good to consider functions of more than one variable. Let's look at considering the temperature T at every point on the surface of Earth. Then this temperature depends on the longitude x and the latitude y of the point P, and it depends on time t. This means that we have a function of 3 variables, x, y, and t. T goes from D to R, which is D is some weird subspace of R3. We could think about. Essentially, we have the surface of Earth, we have every point, and so you're going to get a longitude and a latitude point, x and y, and then what you have is a time t, and usually we're going to start time at 0 to infinity, and then t is going to be inside there. So D is going to be S2, which is a 2-dimensional manifold, so 2 dimensions times 0, infinity. Anyways, we have this 3-dimensional map. All right, the definition of level surface now is completely analogous to the definition of level curve for a function of 2 variables. The set of all points x, y, z in R3 now, such that a function f from D to R, where D is now a subset of R3, has constant values, f of x, y, z is k, is called a level surface of f. Let's do some examples of this. Example 1, we want to find the level surfaces of the function w, which is f of x, y, z, which is x squared plus y squared plus z squared. Now remember, this isn't relevant to the problem. Well, it's relevant to the problem, but we don't need it necessarily. But the graph of f of 3 variables is going to be x, y, z, f of x, y, z in R4. So we can't draw this anymore. I don't know how to draw in 4 dimensions. All I can draw is up to in 3 dimensions. Now what we want to do is use the analog of level curves, so we could use the level curves to get a picture of how to sketch the surface or the graph of a function of 2 variables. We want to play the same game, but now because we can't actually pictorially draw the graph of a function of 3 variables in 4 dimensions or higher in any dimension that we go beyond this, we want to look at level surfaces for functions of 3 variables to get an idea of what the graph would look like in higher dimension. To do that, what are we looking for? Remember now, same as level curves, I write it down every time. Level surface. of f of x, y, z now. It's of three variables. What is that? That will be f of x, y, z. So x squared plus y squared plus z squared equals k. And this will be the square root of k squared. This means that this is a sphere with center 0, 0, 0, the origin, and radius r equals the square root of k. What are those going to look like? They're going to look like concentric spheres centered at 0. And this is what those concentric circles or spheres are going to look like. They're centered at 0, and then they're going to be nested inside each other, and then they cut a window inside so that you can see that there would be spheres nested inside there. For every k, you would get a larger and larger sphere of radius root k. Next question. Okay, example 2, sketch the level surfaces of the function of three variables w, which is the square root of z minus x squared minus 2y squared. What do we do? Level surfaces for f of x, y, z. What do we have? We're setting the square root of z minus x squared minus 2y squared equal to k for some real number. This is if and only if z minus x squared minus 2y squared equals k squared. Solving for z, this is if and only if we get z equals x squared plus 2y squared plus k squared. This means the level surfaces for this function of three variables are elliptic paraboloids, and they look like this. They're concentric elliptic paraboloids for different values of w. Please subscribe by hitting the button right here. You'll get notifications for this series and many other series on our channel. I'll see you next time.